Hello everyone, my name is Ziqi, and I'm going to talk about Fluxonium Qubit today. Yeah, so I will talk about the structure. First, I will talk about the historical overview, and then I will talk about the motivation and comparison to competing technology, then device function, then state-of-the-art techniques. And last, I will talk about challenges for future development. Yeah, so the historical overview of superconducting circuit. Superconducting circuit has the Josephson junction. We talked about that in class. The first one was the Cooper pair box qubit. It utilized the Josephson junction. Boshai demonstrated the first single Cooper pair in 1998. Nakamura designed first Cooper pair box in 1999. The Cooper pair box is basically look like this. The Flux qubit was designed by Terry Orlando from MIT in 1999. We talk about that in class. The Transmon qubit is a major improvement. It was developed by Koch in 2009. It has some advantages, but also some disadvantages. Then we have the Fluxonium qubit over here. It's basically a Cooper pair box shunted by an inductor. It has many advantages. It was first demonstrated by Mancharian in 2009. The difference is that Fluxonium has an inductor connected in parallel comparing to Transmon. Transmon has a capacitor. This inductor is very powerful. That's why Fluxonium has all the advantages that the other three don't have. Yeah, so basically this is a graph of the current superconducting qubit development of the lifetime. We can see that Fluxonium over here has one of the highest T1, T2 value. So basically it's very good. Now I will talk about motivation and comparison. The performance of a quantum processor, characterized by the fidelity of its operations, is confined by the ratio between the operation time and the decoherence times of the qubit. So basically, our motivation is that we want to pack a long coherence time and large n-harmonicity into one qubit. That's why researchers are investigating alternatives and improvements. N-harmonicity means how fast the qubit can complete an operation of a given accuracy. Next are some comparisons. First is Cooper pair box and Flux qubit. They all use Josephson junction, but they suffer from decoherence. They are very susceptible to charge noise. That's for the Cooper pair box, and the Flux qubit is very susceptible to flux noise. Decoherence will introduce errors during gate operations and constrains the number of qubits. Second, they suffer from material imperfections such as dielectric loss. Dielectric loss means it is like a microscopic two-level charge defects residing in the interface oxide layer of a typical thin-film device. As a consequence, each circuit capacitance acquires a non-zero dielectric loss tangent which induces the energy relaxation of the qubit. Then scientists had the Transmon qubit. The advantage is that it uses a capacitor to shunt the Josephson junction. It largely increases the coherence time because it is no longer susceptible to noise. The disadvantage is that for trade-off, it has a very low n-harmonicity. The low n-harmonicity adds more challenges to scaling, since nonlinearity enables logic. Reducing it too much will inevitably slow down gate operations. Furthermore, the Transmon qubits still suffer from material imperfections such as dielectric loss. Here are some advantages for Fluxonium qubits. It has a very long coherence time. It's very insensitive to noise. By shunting with inductor, we will talk about why this inductor is very powerful in the next slide. It has a very high n-harmonicity, from a few hundred microseconds to a millisecond, and it has very low energy relaxation due to its suppressed coupling to dielectric loss. So apparently it has all these advantages that the other three qubits do not have. And we'll talk about why in the next slide. I will talk about device function. In this slide, the diagram of the Fluxonium qubit is over here. It has EJ to be Josephson junction, EC to be a capacitance, and EL to be an inductor. It's basically like a Cooper pair box shunted by inductor. Here are the design parameters. We want the capacitor to be E squared over 2C, and EL to be H bar over 2E squared by over L. These are the energies of the capacitor and inductor. And here are some parameters that we must allow. We must allow EL to be much smaller than the energy of Josephson junction, and EJ over EC to be in the middle of 1 and 10. Here is the device Hamiltonian H. We can see that here is the phi exit. Phi exit is quite important. We want phi exit to be pi. That's the sweet spot described by the author, by the paper. Yeah. And for the inductor is actually constructed by a tightly packed chain of many inductors. The number is n. Yeah, so it's not a single inductor, it's a chain of inductors. And we want to talk about the effect of large inductor. For n junctions, the flux noise suppressed as 1 over n and 1 over n squared. That's given by the device Hamiltonian. And um, in circuit analysis, if for low frequency, we can see from the impedance equation, inductor has very small impedance, so it's basically shorted, and capacitor has a very large impedance, so basically it acts like an open circuit. And the result is that there will be no charge noise. Because of there is no charge noise, we don't need a large capacitance connect in parallel to shunt the charge noise. Since large capacitor is not needed, we do get a very high end harmonicity because the previous low harmonicity basically came from that large capacitance used. Here are some state-of-the-art results. I found them from Guyan's paper. It's very new. February 5th, 2022, basically last month. He talked about the scalable high-performance Fluxonium quantum processor. It was done in Berkeley. So the paper proposed a scalable high-performance quantum architecture based on Fluxonium Qubit. The decoherence-induced error of a 300 nanosecond 2-qubit gate is below 10 to the minus 3. For relaxation time T1 greater than 300 microseconds and coherence time T2 equals to 2 times T1. So basically it has a very long coherence time and a very high end harmonicity. The structure has the following advantages. It has suppressed crosstalk, reduced design complexity, improved operational efficiency. It has very high fidelity gates and resistance to parameter fluctuations. They also programmed a software to control the processor. His paper promised a scalable quantum architecture for future. We can see from the two graphs. T1 it has a very large value around this area for EJ and EL, and T2 also has a very large number. in average. Here are some remaining challenges from the state-of-the-art technologies. First, we have the large shunt inductor problem. Um, this large inductor is very easily influenced by additional decoherent sources. Therefore, we can see Fluxonium qubits need to be operated at a much lower frequency than a typical transmon qubit to reach a comparable coherence time. Second, we have the low energy relaxation. Because the suppression of energy relaxation at low frequency is often accompanied by a slowdown of the 2-qubit gate speed. That's why it's very bad. Third, we have the problem for a large-scale processor. We have the problem of frequency crowding. Fluctuations, yeah, um, where fluctuations in qubit parameters lead to frequency collisions that degrade the performance of multi-qubit devices and subsequently nano-fabrication yield. The the Nguyen 2020 paper investigated this problem by considering the constraints imposed by gate simulations. So here are the challenges, and hopefully in the future we will have methods to improve those problems. Of course, this is a page of my references. Um, that's my presentation about Fluxonium Qubit. Thank you very much.